Welcome to today's panel discussion on syntactic foams research and application, an update from the USA. I'm Nikhil Gupta. I'm a professor of mechanical and aerospace engineering at New York University and host of this event. We want to acknowledge the US aid funding to make these events possible. This virtual panel discussion series is trying to capture the research and development efforts in syntactic foams from around the world. The previous three panels were organized on December 4th, January 14th, and February 12th. The recordings of these panels are available on YouTube. We'll post the link in the chat later on here. These panels are an opportunity to directly ask questions from some of the leading experts in syntactic foams field. We hope the information that emerges from these events can guide some of the future research efforts in syntactic foams and make research relevant to the needs of the industry. We are fortunate to have three eminent panelists with us today. They need no introduction to the syntactic foam community, so I'll keep their introduction brief from my side, and later I'll let them talk from their side. A lot of questions from attendees in the previous panels were about the commercial availability of particles and resins for syntactic foams. So we are happy that two experts are from industry who are joining us today to answer questions like that. So Dr. Vinay Mishra holds a BS in Chemical Engineering from the Indian Institute of Technology, Varanasi, and a PhD in Polymers from Lehigh University. He brings 25 years of industrial experience in various thermoset resin technologies, notably epoxies and polyurethanes, covering applications such as composites, coatings, and adhesives. He is technical sales manager at Jayhawk Fine Chemicals. Right now is focusing on dianhydride applications in high-end thermosets. Vinay had previously held technology and business leadership roles in companies such as ITW, Sika, Air Products, and Dixie Chemical. He is currently a director at the New Jersey State Chapter and a past president of the Thermoset Resin Foundation Associations. Rob Hunter is an applications engineering specialist at the Advanced Materials Division's laboratory at 3M in St. Paul, Minnesota. He specializes in the use of 3M glass bubble products. He has 20 years experience in helping customers optimizing their formulations. His areas of expertise include particle characterization. He has 5 issued US patents concerning the use of glass bubbles in deep water syntactic foams, as well as oil well control fluids. More recently, he has been focusing on glass bubbles for cryogenic evacuated insulation system for liquid hydrogen storage tanks. He has a bachelor degree in chemicals from Augsburg University in Minneapolis, Minnesota. Our third panelist, Professor Guoqiang Li, received his PhD degree from Southeast University, China, in civil engineering. He is currently the Major Morris and Diet A. Anderson Memorial Alumni Professor at Mechanical Engineering and holder of the John W. Reeve Professorship in Engineering at Louisiana State University. He has been leading syntactic foam research for many, many years with special interest in shape memory polymer syntactic foams with functional properties. He is the holder of 10 US patents and authored over 180 papers that have been cited more than 10,000 times. He currently serves as the associate editor for Journal of Materials in Civil Engineering and serves on the editorial board of numerous other journals. I'm pleased to welcome our panelists, and now I request each panelist to take about 5 minutes to give an overview of their work related to syntactic foams. Attendees can ask questions using question and answer utility, and we'll take some of the questions as we go, so you can start asking questions anytime during the panel. So let us start with Dr. Mishra.
Oh, okay. Thank you, Nikhil. Right, I didn't realize I was going to be the first one, but let's see if I can get my screen to be shared. Okay. All right, can you all see my slide?
Yes.
Okay, great. And I believe Zoom knows not to show the video gallery that I have for myself. You're only seeing the slide, not the videos of everybody else, right? Okay, great. Thank you. Good morning, everyone, and maybe good afternoon in case some of you are joining from the east side of the Atlantic. Um, uh, we have a bright sunny day here in Pennsylvania, where I am based in the eastern side of the US. Obviously, Nikhil, thank you for the kind introduction, and thank you for the invitation to be on this panel. It's really nice to join forces with you and with Rob and Professor Lee. And last but not least, Gary, thank you for doing all the behind the scenes work and keeping us all kind of together. So I think you already have heard that I've basically been in the industry for about 25 years, focusing on thermoset resin chemistry applications. Um, for about 60% of my industrial career has been actually as a formulator, where I was a formulator of adhesives or coatings or composites. And the last 40%, I moved up the chain into the raw material supply side, and where my work then transitioned to providing tech support and help my customer base use those raw materials. But basically, I'm a chemical engineer by background with polymers as my main expertise, polymer chemistry, material science aspects, and so forth. Some of you may not be aware of who Jayhawk is. So Jayhawk Fine Chemicals has been around for over 50 years, and the site is in Kansas, right in the center of the continental United States. We are now part of CAB group from Germany, and in the past we've been owned by many other companies, most recently by Degussa Evonik family of companies. A lot of people know us as a custom manufacturer of fine chemicals. We certainly have a reputation in that field, but we have also been very successful in the area of raw materials for high-end composites and thermoset applications. Most notably, we produce dianhydrides and some specialty crosslinkers. I'll focus on dianhydrides for the discussion today. My work right now is technical sales, collaboration with our customer base, sometimes alongside our co-suppliers. Obviously, the kinds of things we do right now at Jayhawk, they are generally high-end composites. And this means that the problems are very difficult to solve by just one entity by themselves. So we believe collaboration is really the key to try to bring solutions to the market for those kinds of things. I see, Rob, you're nodding, so it sounds like you had that same kind of experience. So we love to work with our customers in a collaborative way. And yes, we are focused on high temperature composites, adhesives, powder coatings, and last but not least, syntactic foams. Let me see if I can change the slide. So the key example I wanted to showcase today from our company is a dianhydride known as BTDA. The mouthful name is benzophenone tetracarboxylate dianhydride. It's a solid powder at room temperature, so that sometimes gives people a pause as they're thinking about how to use it, but it works quite well for high temperature applications. And it's been quite a success in high-end thermoset applications. I just want to mention that in addition to use as an epoxy curing agent, it is also used as a co-monomer for even more high temperature polymers called polyimides. For the syntactic foams, so far we've had success in epoxies. Polyimide syntactic foams, I don't have an expertise in there, but certainly if anybody on the audience is interested to discuss that, I'll be more than happy to engage. Key is that this material gives a very high crosslink density once it is heat cured with epoxy resins, and that high crosslink density translates to high temperature performance as TG, as modulus at high temperature, and other mechanical properties. But it is available basically as a fine particle solid powder. And again, if you have questions, please keep sending them. I have two more quick slides. I could possibly save them for later in the discussion, but at least this slide I want to show because when I say high temperature, I want to give people an idea of what we're discussing. Here's an example of some recent data we generated at the Kansas Polymer Research Center. in our neighborhood of Kansas. And this DMA data shows the 10 delta peak of a cured epoxy at 233 Celsius. And so that's obviously impressive, right? But it's even more impressive when you recognize that this system used a very simple Bis-A epoxy resin. Those who are familiar with the systems, so if you're familiar with the Olin nomenclature, this will be DER 383, slightly smaller molecular weight than the, what is the other one? 331, the DER 331 is the more common one, and EPON 828 is the more common one. But basically, it's the same exact molecule, just a tiny smaller in the molecular weight. And then you have BTDA, microfine grade, used at approximately half the stoichiometry, because it gives you such a high cross-link density that we actually say use less of our curing agent so as to maintain the rest of the mechanical properties of the polymer. And with that system, you get a very high TG. Another thing you may notice is that the storage modulus shown in the green curve, it starts out in a normal, as expected, glassy region. And then as it comes to the rubbery plateau after the TG, it actually stays pretty high. Typically, you expect at least a 2 or 3 orders of magnitude drop in the storage modulus at TG, but this system is extremely high in cross-link density, so your modulus drops barely an order of magnitude at around the TG. And that's another indication that it's a very, very highly cross-linked system, to the extent we help our customer base to formulate the products properly to take off the brittleness that may come from that cross-link density. I have one last slide, and that's specific to the syntactic foams. This work was, this is part of a project that was run at the University of Alabama in Professor Brian Pillai's group. At that time, actually, I was at Dixie Chemical Company, and I was collaborating with Jayhawk Fine Chemicals, to give you an idea how small the world is. And Dr. Gary Gladys, who's been on the panel before here, he was my colleague at that time at Dixie Chemical. And this project, we actually proposed that the system does not use the straight BTDA powder dianhydride, but use it in combination with a liquid monoanhydride. In this case, we used nadic methyl anhydride. And the idea was that the BTDA can give you a very high temperature behavior, high TG and so forth, but the liquid NMA anhydride will act as a reactive diluent and improve the processing properties for the syntactic foam formulation. So this system, of course, Rob, you'll recognize one of your products here. We use microbubbles at 20% by weight in the overall formulation. And you will notice that with, again, a very simple Bis-A epoxy resin, we were able to get a TG of about 200 Celsius. And then, we actually had other temperatures we were able to reach based on what we were trying to achieve in the project. There was some compressive strength data, flexural strength data generated as well. I don't have that handy for this discussion, but for anyone who's interested, I can pull up that data and share that with you after the panel discussion is over. Well, that's all I have for now, and we can discuss later after the introductions. Thank you.
Thank you very much, Vinay. Rob, would you like to go next? You are on mute.
Thank you. Thank you, Dr. Gupta. I needed to unmute myself and share my screen. So I believe I am in presentation mode, I hope. Close enough? Good.
Yeah, we can see your slides. You can put them in presentation mode if you want.
Yeah, I was trying to do that. There we are. Thanks. Thanks, everybody. And thanks, Vinay, for that excellent introduction. And I echo your thoughts of thanking the organizers and our panel and our watchers and listeners. So good morning and good afternoon again, everybody. Dr. Gupta gave me a great introduction. Thanks. My name again is Rob Hunter, and I have chatted with practically everyone in the US and many other parts of the world about the use of our hollow glass microspheres, or glass bubbles as we call them at 3M, particularly in deep water offshore, and syntactic foams, of course, in general. So we call the products glass bubbles, and I titled this presentation in this slide, Glass Bubbles for Density, Thermal Conductivity, and Dielectric Constant, and Dissipation Loss Minimization. And that last part is going to be one of the areas that I'll focus on in my remarks toward the end. We're getting a lot of interest. There is a great deal of activity in the world in the new 5G cellular system and semiconductor in general. So we are offering the marketplace high strength, low density hollow microspheres, hollow glass microspheres. We have glass that we've been developing for decades, soda lime borosilicate glass, which imparts virtual insolubility in water and broad chemical inertness. And as most people on the call can imagine or can appreciate, low true density imparts low thermal conductivity, and maybe a lesser known feature of what low density imparts in general is low dielectric constant and low dissipation loss or dissipation losses. So we have many products, several different portfolios, and I tried to present a subset to keep the story a little bit simpler and focusing on the lowest density products that we offer, which are usually of particular interest to the syntactic foam community, and sort of cut it off arbitrarily at under half the density of water at 0.46, which is the target density for this product at 16,000 PSI. So as you can appreciate, in the way the little cartoon drawing shows, there is a thin wall, unicellular, single hollow microsphere. Of course, there's going to be a particle size distribution that will accompany the strength and density envelopes or bookends, if you will. So let's see if this goes to the next one. Some people might be interested in a very brief timeline. I'm not going to read all the words, but in the early 60s, there was work in 3M on hollow glass microspheres. And so we talk about the decade of the 60s as being really only syntactic foams, predominantly military, deep water, that is to say, Navy and so forth. A fun little thing is the use of glass bubbles in bowling balls to make, lightweight bowling balls. In the 70s then, as oil and gas moved offshore into deeper waters, drill riser buoyancy became critically important. Other more construction uses of our products in cultured marble, composites of various kinds came into play, and a very unusual, particularly specific use of our products is to sensitize ammonium nitrate, which are called emulsion explosives for civilian and mining activities. That's a very specific use of our products. There's so many different things we can talk about with respect to materials. In the 80s then, our retired glass scientist invented a new sort of glass which improved the strength to density of our products. And then just more developments over the decades. Deep water oil and gas, wet insulation pipe coatings became critically important for deep water flow line pipe insulation. And into this century, oil and gas continued to grow with low density oil well casing cement slurries and other well control fluids. Things that reject infrared radiation and solar reflective paints being discussed. And then we had kind of a process breakthrough, which allowed us to develop even higher strength to density glass bubble products, which one of the things that Vinay presented was XLD 3000, one of my favorite products that I had a hand in developing. and especially the applications for XLD 3000. But these newer products have smaller particle sizes and narrower particle size distributions, which really people like for their beloved Class A finishes. That's like an automotive Class A finishes in sheet molding compound or SMCs and other materials, really critically dependent on small bubbles. And speaking of small bubbles, now here we are in the 2020s. Thank goodness 2020 itself is behind us. Smaller top size is particularly important, so cleaner, tidier products. And we've just recently launched these two things, which I can talk about at a little bit more length here as I move through my slides. Many people on the call perhaps have seen these maps where we present on the y-axis the isostatic crush strength, and you always want to choose a hollow microsphere on the basis of strength versus average true density. We don't use the term specific gravity at 3M because that implies that every particle has the same exact density, but a gas pycnometer will give you an average volume, which of course will give you an average true density. There's that XLD 3000 way down here at 3000 PSI. This presentation cuts off at 16,000 PSI with the new S4630. And then here's the other new product. Now this is a new surface treated product with vinyl silane at 0.32 density and 6,000 PSI. So these in red are the newest, absolutely the newest products. And I want to feature of interest specifically perhaps to the 5G and semiconductor world. The newest low density product is way down here at 0.20, the K20HS, HS for high strength. A 750 PSI bubble at 0.20 target density may be of particular interest to the deep water or the syntactic foam community. Just a quick note about the new products for 5G and semicon. We have 5 products. Our Korean factory is behind my Zoom panel. We have 5 factories throughout the world. And here are the specific details, lots of numbers. Nobody should have to memorize this. We can get technical information sheets out to anybody interested for the very high strength, very small S4630, and the lesser strength, but still pretty high, and slightly larger S3240-VS for vinyl silane, and the dielectric constant and dissipation factors at about 10 gigahertz are down here, very low numbers. So I think that's all I really have to say today, except, oh yeah, of course, I've got to put in a plug for the legacy floated products, the floated and surface treated products, which are some of our oldest products, as you might guess by the first one here, the product prefix letters A and D and H. These products were made from the earliest process that we ever knew about, which literally separation by flotation to benefact the strength to density ratio, and these products are still all available. And with that, I want to respect time and thanks everyone. So I'll turn it back over to you all for the control.
Thank you very much, Rob. Excellent
Thanks.
information on your slides. Dr. Li, would you like to go next?
Yes. So let me share. All right, so I think everybody can see it. And first of all, I would like to thank Dr. Gupta and also Gary Mack for organizing this panel. It's really an honor, to sit with the distinguished panel members from industry to talk about synthetic foams. My group also worked on synthetic foam, but it's a small, different direction. So we work on shape memory polymer based synthetic foam, and definitely want to know that what is shape memory polymers. It is quite an interesting topic in the past 20 years for the shape memory polymers. So basically, there are many types, with time goes by, many times shaper polymers has been, created. Okay, for example, you have one-way shaper polymer, two-way shaper polymer, multiple shape shaper polymer, all the type of things. But here today, I just talk about a one-way shape memory polymer-based synthetic foam. Okay, what does one-way shaper polymer means is that if you deform the polymer into plastic deformation, this deformation can be maintained forever, just like other materials when they are deformed plastically. However, under a certain stimuli, okay, like heat, light, moisture, pH, all that type of thing, this plastically deformed material can return to the original shape. Okay, so we call this one as one-way shaper polymer. So what we do is that you can see when you prepare shaper polymer-based synthetic foam, it's just like what you do as a conventional thermoset polymer-based synthetic foam, right? You mix the glass beads or other microspheres with a resin, and then you mix them together, you add the hardener, and then you cure it, okay? Even the mechanical behavior is very similar to the conventional synthetic foam. For example, if you look at the red line, you can see the elastic deformation yielding, plastic flow or buckling of the microspheres. You can see even some crush, and then finally you see the densification. Okay, that's exactly the same as a conventional synthetic foam. However, what is different is, just as I said, after deformation, this deformation actually can be restored. Okay, so here I show you a typical stress-strain relationship. Okay, I divide it into 5 steps of the deformation. You can see that you load the synthetic foam until you come to the yielding point, and you may see a little bit strain softening, and then plastic flow, and then densification. Okay, so there's a loading process, and then you can hold the loading for a while. You can see some stress relaxation in the step 2, and then you can unload. Okay, removing the loading, you may see first linear elastic, nonlinear elastic spring back, or even viscoplastic or viscoelastic spring back. Okay, so step 1, 2, 3, 4, we call it programming, or we call it the education process, okay, to make the synthetic foam into a new shape. Okay, in step 5, here I show you that if you try to heat it up, the material will try to recover. Here I show you that instead of recover the shape, I show you it can recover some stress. Okay, that means the type of synthetic foam you can play with as a shape change. You can also use it as actuators, right, to do some work to other products. All right, for this synthetic foam, if you put as a core material for sandwich structures, for example, you do a low velocity impact test, you can see that the load and the energy history with time also exactly the same you see for conventional synthetic foam. Of course, the difference is that this type of damage by low velocity impact will be able to self-heal due to the shape memory effect. So now I give you a brief introduction how the idea works. So basically you start with a synthetic foam, which using the shaper polymer as a matrix, and then you can distribute some thermoplastic particles or fibers as a heating agent. Okay, and then you heat it up, or even not heat it up, you can do a compression programming. You can see you add compression first. So after you deform to the level you desired, you you're cooling down, you remove the load, you can see the volume of the synthetic foam has been reduced from here to here. So this shape can be put in service. Assuming during in service, you have impact, you create a large crack. So now I want to show you that how to based on the biomimic, the human beings, your skin, can heal, right? If you cut, the cut can be healed. So basically we are trying to simulate that process. Okay, what you do is that you heat up locally surrounding the crack. You know that once you come to a certain level of the temperature, this shapemer polymer matrix will remember the original shape. That means it's here. So that is trying to expand in volume. However, surrounding this hot zone is cold materials, so that the free volume expansion is not allowed. Instead, it must be pushed inside the open space. So in such a way, you see the crack can be narrowed or even closed. And then the distributed heating agent, thermoplastic, can be melt, can flow into the narrowed crack. So if you're cooling down, the physical entanglement will be established so that you achieve the molecular level self-healing. Of course, some new things that we developed is that we use covalent dynamic bond for the shapemer polymer. So in such a way, there's no need for the heating agent. Okay, once the crack is closed, a shape memory effect, the polymer will be healed autonomously by itself. All right, so here I show you a couple examples. This one you can see, this is a synthetic foam. We cut a crack about 50 microns. So when you heat it up, you can see the crack fully disappeared. The material is healed. Okay, so here is using the shapemer polymer-based synthetic foam as the core of sandwich structure. You can see that this is the original structure. This is an ultrasound C-scan image. Okay, this is before impact. After impact, you have this damage zone. And then after heating, you go to second impact, seventh heating, all the way seventh impact, seventh heating. So basically, this type of damage heating capability is repeatable. Okay, it can heal large open crack, not just macro cracks, but also is repeatable. The reason is that the shape memory and also the heating process is a physical change process. There's no chemical reaction related. That is why it's repeatable. All right, we also did some solid mechanism modeling. You can see this basically is the microballoon. You have a interfacial transition zone, and then you have the polymer matrix. So we can establish a 3-layer built-in model, and then we can introduce the viscoelasticity, viscoplasticity, and thermodynamics, and we model this polymer. So basically, you can see this strain change with time. You can see loading, holding, removing the load, and then shape recovery. So the model definitely can reproduce the experimental result. And we also did the 2-dimensional loading. For example, in this device, you can see in vertical direction is compression, in horizontal direction is tension. Okay, so our model, again, can reproduce the 2-direction programming and shape recovery process. Okay, so recently we also use a 2-way shaper polymer as a matrix, and we also extend the applications to not just as the core for sandwich structures. We also extend it to, let's say, as a sealant for cracks and joints. And we are looking for more applications and more potential to collaborate with industry partners. So we only have 5 minutes. I cannot introduce more, but here is a list of relative publications with shape memory polymer-based synthetic foam. Thank you.
Thank you, Dr. Li. So there was one question from an attendee that in the slide where you show the impact and the recovery, the images are red and blue color. So what do those colors represent?
Okay, so let me to see if I can. All right, so let me see if I can reshare this slide. Okay, the colors, you know, that is the ultrasound, right? It's a reflection mode.
Okay.
It depends on the density of the material and also reflect the signal of the ultrasound. So for example, for the white colored, you know, this one I show this is a damage because the signal basically ultrasound just pass through it, cannot be reflected. Okay, for the blue colors, usually the density is a little bit small. The red colors is the highest density. Okay, so you may wonder why the color change during the process, right? During different times, because each time you have the damage and you also have the heating process. That means you heat it up. So the material may adjust the microstructures, and also even the signal we use may not be the same each time. Okay, for example, we put the sample in the water bath, right? Even the distance from the surface, all this may change the color. But what's important here is a white spot. That is an impact damage, and after heating, basically that spot disappears.
Thank you. So Rob, I wanted to start with a question for you. So you showed these new particles, which is quite exciting. So what exactly is different with these new particles? Is it the glass composition, or is it the processing method which is different, or you are just selecting particles which are better and discarding more damaged particles?
No, good questions and good insights. So I'll start with the glass itself. We use one glass for all of our products. We're always considering and researching different glasses. So that could change, but as is today, still we're using the same soda lime borosilicate glass. The two new products, which I myself will attempt to share. This one, if I could, and then skip down to these. Can we see my screen now? Great,
Yep.
Thank you. Yep, so the two new products, just real briefly, wow, it really doesn't want to go into, okay. The main differentiator is we're warranting a tiny fraction of top size. That's the main thing. So I'm not a 5G or semiconductor expert. This is new territory for me, but we have heard loud and clear that large particles are detrimental to many applications. And so we take pains to eliminate the top size fraction. So we're warranting by our new test 0.05% by weight retained top size particles over a 53 micron equivalent mesh size. That's the principal thing. And we are also, water, we heard loud and clear, is an issue as well. So these products are warranted to be less than 0.3 or 0.35% water by weight. So those are the two main differentiators: top size control and somewhat drier products.
Okay, and a follow-up question is that how do you measure the isostatic crushing strength of these particles? Because a lot of people just care for that for these structural applications.
Oh, absolutely. Yeah, no, you have to choose from our product portfolio on the basis of strength. Absolutely. So we have developed over the decades two different methods, and we use one or the other in factory and laboratory operations, factory for quality control and certification purposes. So we either do gas phase pressurization testing with change in true density by gas pycnometer, calculate a volume percent loss. So when we say, for instance, that this new product, well, that's the way that we do it for lower strength products. For higher strength products like these, We use a liquid phase test where we have purpose-built custom equipment which exposes the sample dispersed in a liquid to 2 pressurization cycles with very delicate control of change in volume versus pressure. And so we're warranting, say, what pressure does 90% of the volume survive? So when we say greater than 16,000 PSI, we're trying to say, for instance, that the new S4630, 90% of the volume of the spheres will survive 16,000 PSI in this test, or in this case, 6,000 PSI.
Okay, thank you.
You're welcome.
When I had a question for you, that what's new in the sets and thermoplastics, especially from resin and hardener point of view. And the reason I'm asking this question is, people are always trying to do new things. 3D printing is big thing coming up. Like everybody wants to 3D print these underwater vehicles right now. So what kind of demands do you see on the resins and hardeners right now?
Yeah, so obviously any demand, new demand generally means some sort of an extreme from the application point of view. Obviously, I've spoken a little bit about high temperature. So anytime you have a higher temperature environment, say for deep sea oil drilling related application, where in addition to buoyancy, you need thermal insulation as well at high temperatures. That's one area. And the other would be perhaps rubber toughening or toughening of some of these technologies which are required to have rigidity and high temperature capability, but they need to have substantial fracture resistance that current technologies are not able to offer. So I'm more knowledgeable about thermoset applications, less so on thermoplastics. So let me focus on what I know first, and maybe I'll venture into thermoplastics if I'm brave enough, let's just say. So I've already explained that, that's where we play is the high temperature area. I would say it's not so much new technologies that are available now, but maybe technologies that have been around that have been underutilized to this day in syntactic foams. So one example would be, like you said, 3D printing. So actually, I believe Gary Gladys already talked about the CRADA at the Oak Ridge National Labs that he was involved with it. And I was his partner at that time at Dixie Chemical, and we ran that project. At the time I was involved with the project, we hadn't ventured into the syntactic foam characteristics. We were still doing the 100% resin type formulation at that time. But the next step really immediately was going to be to incorporate the micro bubbles, I guess, glass bubbles, as Rob likes to say. And I think the challenge really was in getting it done, getting it to extrude through a tiny nozzle to be able to build a large part. And the bubbles were going to help lower the density so you can build a large structure without the weight of it bearing down on the dimension, so you can get the dimensional stability. And then the resin matrix was going to give the high temperature capability that Oak Ridge was quite interested in at that time. So that's kind of one new area. The other thing I was just going to say was, and obviously anybody wants to go higher than current epoxy technology, we invite them to reach out to us because we believe we have a we have a solution in our dianhydrides, BTDA. Let me bring my slides back up. Maybe I can share that so people know what I'm talking about.
Yeah, a follow-up question I would have is that what kind of applications do you see that require high temperature capabilities?
So, so in oil drilling applications where they are getting into deeper oil wells or higher temperature processing, in addition to buoyancy, you need that high temperature because I think, Rob, you and I were having a chat just the other day, right? Where the fluid has to be continuously moving. And if there is any kind of a stoppage upstream, up the rig, then the material can start cooling down very rapidly. Ocean water is very cold at the bottom. So the insulation has to be able to not only provide insulation, but the insulation that is closer to the inside of the, closer to the actual pipe can get very hot, and you can have long-term damage to the matrix from that high heat exposure. So that is like a pretty intense requirement in the industry from that perspective.
Yes.
And then you have the aerospace, right, aerospace applications where you need the lightweight and you need the mechanical strength of the composite part that is, that requires the combination of those kinds of things. Last but not, I mean, I'll come back to another application on high temperature a little bit later, but I want to just clarify one more thing. Epoxy toughening is another area that I believe syntactic foam thermoset chemistry has not fully taken advantage of. And I'm not sure why, but I have guesses. I think the traditional epoxy toughening technologies were either the CTBN technologies, which are high viscosity liquid rubbers that are pre-dissolved in the formulation, and they raise the viscosity of the overall formulation. I believe that might have been a reason that they were not so widely used in syntactics. The other technology was core shell impact modifiers, which are powders, and they also raise the viscosity of the medium. So both of these technologies had that issue. I think there's a newer technology. It's been around for at least 5 years now from Olin, I would say. Again, I'm not endorsing anybody's product, but I know that's a product that is out there in the industry. It's relatively new for a toughener. It's a low viscosity material. It's like a block copolymer technology that will dissolve into the resin matrix without improving your viscosity, without increasing your viscosity too much. And then it phase separates during cure to give you a toughening. I believe that's a underutilized, relatively new toughening technology. If its use is, if it's used in syntactic foam epoxy systems, it probably will open new doors because it'll improve fracture resistance for under a lot of mechanical stresses.
Thank you. My next question is to Professor Li. And you've done a lot of modeling and simulation studies and developed models for syntactic foams, quite sophisticated work for shape memory polymers. But one thing we notice a lot of time that this work mostly remains of the interest of academia and does not get to developing tools that industry can use or users can use them for product selection. So how is simulations and theoretical studies, how are they helping the users and the industry? Would you like to comment on that?
Yes, I think that's a very good question, for this community to develop some simple tools and engineers can utilize for design or prediction of the properties. And if you talk about the shipping polymer-based synthetic foam, the shipping polymer itself is already very complex in order to fully consider the programming and the shape memory process. Usually, for example, if you based on the viscoelasticity and viscoplasticity theory, the model may introduce over 30 or 40 parameters in order to fully represent. So I would say that for shipping polymer at this moment, the challenge is that how to better understand the physics governing these materials so that the model parameters can be significantly reduced so that you can really have some model which is useful. For conventional synthetic foam, I think some simple micromechanics model may work. Like the models based on Ashby's equivalent theorem mechanics. That one basically is in terms of prediction of the modulars and also tensile strengths. I think that one is accurate enough in terms of a preliminary design. And the model itself is close formed and it is easy to implement probably just seconds of computation time. However, just as I said, for cheaper polymer based, there's still a long way to go in order to get models which can be utilized by engineers.
Thank you. Rob, I had a question for you. Actually, Professor Lorenzo Bardella asked the question. I want to generalize this question more. So 3M has a lot of data on particles. You are the largest manufacturer of these particles for decades now. A lot of this information on the particle size distribution, wall thickness, defects, and all that, that can be used to give pretty good models and predictions based on the mechanics that we have developed over the years. How do you work with researchers, or what are the possibilities of sharing some of that data so that we can help you and also help the community of users of syntactic foams?
Wow, that's a broad question. That's a big question. Let me see if I can understand it. So it's true for sure, of course, that we've been making and developing hollow glass microspheres, and always the engine that drives us, as we understand the value proposition for most applications, is maximizing the strength to density rate relationship. People usually want to minimize density, and then they need microspheres that survive a process or an end use condition, deep water, famously high pressure applications, where the syntactic foams have to have mechanical properties sufficient to the task. So the question is, how can the amount of data that we have concerning our microspheres be shared, I think is what I understood.
Yeah.
That is a challenge, because we make these products available for commercial sale against key to quality characteristics of strength and density. We are getting a little bit deeper now into particle size based parameters or issues, a little bit with moisture when it applies to critical applications as well. I'll have to noodle on that. I can't come up with a thing on the spot of how we could make that easier, or how to get our arms around that. That's a challenging question.
Yeah, because a lot of us get small sample from the company, and then we do the particle size analysis, density analysis, and all that. And then we fit a model on top of that data, but you have more reliable and a large trove of data available already. And now we are moving into machine learning that can benefit from that large data set to, it's a situation where company can be benefited, the users can be benefited, and researchers can just provide better information and models.
Well, I think our product information sheets try to give people the central tendency for what the average particle size. If it's coming down more to particle size, then that's something that we could consider. And if it's a question of what our process capability indices are around strength and density, that's something else that we discuss with specific customers from, quite often. Sort of the marriage between what are we actually able to deliver versus what our specifications are. So it's a fascinating question, and I honestly don't have the quick answer today. Sorry.
Sure, but I just wanted to put it on your plate there for thinking at some point. And same thing with Vinay, with a lot of industry experience, you have moved from in different companies and different roles. And now syntactic foam field is at a position where, the oil and gas sector is probably not a growth sector in long term. Wind energy, where syntactic foams are getting used a little bit, but that's a huge growth sector. So how do we get into those places, keep ourselves ahead of the curve so that syntactic foams can be used when people are ready to use them? So those are the things that I wanted to bring to you, to industry. And that was my motivation to invite you to the panel. And Professor Li has done a lot of mechanics, and we have developed models. Professor Bardella is here. He's well-known expert in mechanics. So this could be a possibility to help out the user community in ultra deep water or wind turbine or other growth sectors which are out there. Unfortunately, an hour passes pretty quickly. We have only 3 minutes left. And if you would like to make any closing statement for a minute from each of you, that would be great. So can we start with Dr. Li?
Okay, so in closing, I think for the next step for shipping polymer-based netted foam is that first, I think we need to further to develop multifunctional polymers, shipping polymers with integrated properties like self-healing capability, like excellent shaper memory, high recovery stress, fire tolerance. All these have been integrated into this one simple polymer using machine learning. And the second one is trying to develop some models, simple models, which can be utilized by industry.
Thank you. Vinay?
Yeah, thanks, Nikhil. So my takeaway, guess message that I'd like to send out is that collaboration is key. Anybody who's working in syntactic forms, universities are, of course, quite open to collaboration, but I would say to the companies who are developing the formulations, they tend to be close because of, obviously business reasons, but the best results are obtained when there is collaboration with agreements in place and so forth. I mean, we ran out of time, so I didn't mention this, but there was a nice syntactic foam wall panel that was designed as part of a collaborative project back when I was at Dixie. Gary Gladys and I worked with epoxy syntactic foams, Novel Tessier, core composites, clear carbon composite. There were like 5 or 6 companies actually were trying to build this damage resistant, blast resistant wall panel for making blast resistant building for all kinds of applications. And I know it would not have been possible if just 1 or 2 companies were working together. So collaboration is my request to all parties.
Okay. Thank you. Rob?
Thanks so much, everyone, for the opportunity to talk about our products that fit into this space. It was a pleasure, and I agree with Vinay. Collaboration and cooperation are so vital to moving projects forward quickly as possible. And what we do at 3M to help people navigate our product portfolios is have one-on-one conversations at all times, of course, as well as provide as many samples as people could possibly need of our products to see what they can offer. So samples are readily available. I am easy to find, and I'm looking forward to continuing the conversations. Thanks again, everybody.
Thank you very much. So I wanted to thank all the panelists for spending this hour with us today and providing us with excellent information. I want to thank USAID for funding these events. And I think the biggest thanks goes to my PhD student, Gary Mack. He spent a lot of time in putting together these panels, inviting panelists and sending out emails to everybody for registering for the panels and all that. We are going to put this online on YouTube, the recording, and it will be available for people to watch later on. Thank you very much. And I thank all the attendees for coming to attend this panel today. And once again, all the panelists, thank you very much.